Hi, everyone. Thanks for this opportunity. My name is Kloster. This is joint work with my supervisors at Lincoln Lab from last year, though now I'm at North Carolina State. And the title is Scaling Overlapping Clustering, but I think of it more as a broader problem of scaling graph analytics in general. And this is just a case study of the particular problem of an overlapping clustering method, namely linked clustering, which I'll describe. How can we make it faster? Because a lot of graph analytics don't scale so well. Community detection problems aren't exempt from that. How can we make them faster? And so what I'm going to talk about is the importance of having tight complexity analysis of your algorithm and how that can help identify bottlenecks that you can hopefully overcome to make your algorithm faster. And this is something you see in, I think, a surprisingly small number of papers, tight complexity analysis of the algorithms. And people keep talking about needing their work to be faster on larger graphs. So I think this is something close to my heart, at least. Like I said, I'll focus on an algorithm that is not mine, called linked clustering, from a 2010 paper on Bagro and Lehman. And the basic idea is, what if we partition the edges of a graph and then form communities from the edge community memberships? So each node then becomes a member of all communities that its edges are in. And so here you can see sort of the canonical example of node clustering doesn't really know what to do with this node here, but edge clustering allows this node to take part in the three obvious communities in the graph. So talking about scaling an algorithm, we want to know, what does it scale with? So one of the things we're going to look for in the next few slides is, how is this linked clustering algorithm really scaling? What determines how quickly it runs? And a lot of papers tend to look at how their algorithms scale with number of edges in a graph, number of nodes, maybe max degree plays some part in the scaling, or something, Tammy called them wedges. I also call them wedges, these paths of length 2. To talk about how the algorithm scales, first we want to overview it just a little bit. Again, this is not my algorithm. This is just the algorithm that we try to make faster. So the basic idea is, first, compute similarity scores for every pair of edges in the graph that are touching each other. And so right here is an example of what I mean by edges that are touching each other. So compute all of those edge similarity scores. And I'll say in a bit what I mean by similarity score. Then you sort those similarity scores so that you know which ones are most highly similar. And then you start merging together first edges that are highly similar, and then clusters that contain highly similar edges. And then you keep doing that until you decide you've reached a partition that satisfies whatever criterion you have, which is not so important for this talk. So high-level overview. Getting a little bit down into the nitty-gritty, when you compute these edge similarity scores, what are you really doing? The original authors recommended using the Jacquard index, or Jacquard similarity score. So for a pair of edges that are touching, you look at the two endpoints that are not touching, and then look at the Jacquard similarity score for their neighborhoods, which just looks like this. It's not so important you remember the details, but remember that it's a fraction of integers. That'll become important later. Once you've computed all those, note that the object for which we compute a similarity score is a wedge. You sort all of those wedges by their similarity scores, and then start combining clusters, like I mentioned. And here are a list of edges sorted. And then you start combining edges B and C because they're most highly similar, and so on until you decide to stop. OK, how can we make this faster? First, tight complexity analysis is going to let us see what the real bottlenecks are, what the real problematic graph features are, and then how we can address them. So it turns out that these two phases are very fast, so we don't have to talk about those. But these two steps are the dominant subroutines. To compute the similarity scores for all wedges, you at least have to do an amount of work comparable to the number of wedges, right? Because you need a similarity score for every wedge. So this is a lower bound. It turns out we were able to prove it's also an upper bound, so that is tight. Which means that you have wedges, number of similarity scores to then sort. And anybody will tell you, sorting, that's n log n, right? So the dominant subroutine in this algorithm is sorting, which really shocks my collaborators and I, because we do sorting as a subroutine in almost every graph analytic, I feel like. You know, page rank, if you're ranking things, then you're doing sorting, right? So this came as a real shock to us that the dominant subroutine is something that could be a dominant subroutine in a lot of graph analytics. So how do we address both of these problems? Okay. First, I want to point out that the fact that we have to deal with wedges means anytime you have a large degree node, you introduce a whole lot of wedges. So one of the bottlenecks we're identifying here is that nodes of large degree, which I'm going to call hubs, produce a lot of wedges. So nodes of large degree are bad. This is very common to a lot of algorithms, but this will become important later on. Oh, I should say, the reason a hub introduces a lot of wedges, at any particular node, look at this green node here, how many wedges are at that green node? Choose any two of its neighbors, and you have a path of length 2, so that gives you a wedge. So degree choose 2 is the number of wedges at any particular node. All right, so what have we learned? Sorting is the dominant subroutine, just to review. Runtime of this algorithm scales with wedges, really with a sort on wedges. Maybe we can do something about that. And hubs are a real big problem for us. So these are the bottlenecks, hubs and sorting. Those are the bottlenecks that we want to address. And this wouldn't be possible without that tight complexity analysis that I really want to emphasize, I think is important. Okay, so I mentioned Jacquard similarity. You don't have to remember exactly what it is. Keep in mind that it's a fraction, and it's a fraction of numbers that are inside this interval 1 to maximum degree times 2. What that means, the reason that's important, is it means the set of similarity scores that we might be producing, even though we might have a billion different wedges that we're giving a score to, the set of different values that their score might be is very small. It turns out to be no more than max degree squared. It can be actually a lot less than that. That means that we can actually sort in linear time if we don't use a comparison-based sorting algorithm, which are sort of the go-to, your quick sort, your heap sort. If instead we use something like what we cobbled together is a sort of a split between bucket sorting and counting sorting, which we call shelf sort. And that enables a linear time sort. And we were able to do that just by looking at the structure of the problem. The set of things you're sorting aren't really that, I'll say, diverse, meaning you're not sorting arbitrary values from 0 to infinity. They're fractions between 0 and 1, and we know what their numerator and denominators are. And that brings down the dominant subroutine from wedges log wedges to just wedges now is the obstacle for us. And like I mentioned before, hubs introduce a whole lot of wedges. All right, so visual to give you an idea of what shelf sort is. Basically, given a Jacquard similarity score, you know it's non-zero. Take its inverse, and then take the closest integer. And it turns out it'll be guaranteed to fit into one of those shelves between 1 and 4 times max degree squared. And so that enables linear time sorting. Right, so hubs are a big problem because they make a lot of wedges. So I'm going to try to convince you that sometimes the best thing to do when you have a big problem is to ignore that problem. And what I mean by that here is we're going to remove from the graph all of the biggest hubs. And I claim that that's OK to do for a few reasons, depending on your data. Often, hubs are meaningless. Think of spam email accounts that email everybody in a communication network. That doesn't introduce any clustering information. Or things like Obama and Bieber on Twitter. Everybody follows them. So are they really introducing any information into our clustering? There are examples in biology as well, genes that tend to appear a lot with all other genes. So I hope I've convinced you that sometimes it's OK to ignore these large degree nodes. What we end up doing is removing them from the graph and running much more quick algorithms on what remains. It turns out sometimes that it can even improve clustering quality because large degree nodes can obscure clusters by connecting disparate clusters. OK. So what's our procedure for this? Remove the nodes. That's it. Just ignore them. If they're important to you and you want to know how they relate to other clusters, we do have a procedure for adding them back in just to the clusters to which they most strongly connect. You can do this quickly. And that's the whole procedure. It's as easy as it looks. A rare case of an algorithm that's as easy as it sounds. What's the result here? So structure in our sorting, and we're able to sort faster because of that. Just this idea of following the narrative of your data sets, remove the problematic nodes, these bottlenecks, these hubs that are creating so many wedges. And what's the end result? What you're looking at here is runtime information for a few different versions of the algorithm linked clustering. The red dots are the original implementation that the authors introduced. And then a couple other competing algorithms, InfoMap and BigClam, which were state of the art at the time they were introduced. And you're seeing how they scale according to wedges. Red, the original implementation, is several orders of magnitude slower than purple was our optimized version that introduced the shelf sort and a couple other things that obtained the actual lower bound for runtime. So you get several orders of magnitude speed up just by doing that. Removing hubs introduces an additional factor of roughly 30 or so, adding up to about 10,000 times faster on these larger billion wedge networks. And I should add that going from red to pink to blue totally preserves the quality of clustering. When computing the quality of clustering on networks with ground truth communities, no loss in clustering quality compared to the original implementation's quality obtained. I also want to point out that this shows how the runtime scale with wedges. We were actually able to show, so I mentioned already that linked clustering we proved scales exactly with wedges. It turns out wedges does a better job of describing runtime of BigClam and InfoMap compared to using edges to describe their runtime. So it seems like there might be something to this looking at how other graph features other than just edges describes runtime scaling. So just to summarize, if you're scaling any graph analytic, although the case study here was just for overlapping clustering, you might consider performing tight complexity analysis so you can identify what your real bottlenecks are. They might surprise you and might be something simple like sorting. Thank you.